Good morning. Today, I'd like to finish up this section on analytical geometry by thinking about some typical geometry problems in three-dimensional space. We will describe a straight line in the following way. We need to know a point of the line, which I've indicated as x0, y0, z0, and we also need to know the direction of the line in some way. The way we think about these things now is that we'll have a vector that points parallel to the straight line. If I have any other point on the line, I can form the vector from the known point to the new point. It must point in the same direction as vector v. It must be a multiple of vector v. So depending on what the other point is, I'll call that multiple t. T will vary as I look at different points on the straight line. If you write out what that vector equation means and then split it up into components, you find out that these three things must be true. For many purposes, it's useful to write them in this format. This is very strongly reminiscent of the point-slope form of the equation for a straight line in our previous work. These numbers, a, b, and c, very roughly speaking, represent sort of, kind of slopes. The derivative of x with respect to t would be a, the derivative of y with respect to t would be b, and with respect to t, the derivative of z would be c. These three numbers, a, b, and c, indicate the direction that the line is going in. The simplest kind of question you can ask here is find equations for the straight line. Find equations for the straight line that passes through two given points. Here, one of the points has coordinates 1, 2, and 3. The other has 5, 3, and 9. If I knew a point on the line and a vector that points along the direction of the line, I would know everything that I need to know. So firstly, knowing a point on the line is no trouble. We know that one. Or if we felt like it, we could say we know that one too. The vector that goes from one of these points to the other one points along the direction of the line. That's going to be our v vector. A vector parallel to this line is 4, 1, 6 component-wise. I'll use the point P as my known point, so x0, y0, z0 are 1, 2, and 3 respectively. Of course, if I had used Q instead, I would have written 5 plus 4t, 3 plus 1 times t, and 9 plus 6 times t. I would get equations that superficially look different, but in actuality are the same. If a person were paranoid, they would make sure that there is a single t number so that when you stick it into these formulas, you get point Q back for an answer. Let's be paranoid. I have three things that I have to demand of a single t number. If it turns out that these equations are contradictory, then I've made a mistake someplace because point Q isn't on the straight line that I've written down. On the other hand, if there is one single t value that makes all three of these things true, this demonstrates that point Q is a point of this line. The top equation obviously says 4 equals 4t, so t needs to be 1. The second equation says 3 minus 2 is 2 plus t minus 2. 1 equals t, t equals 1 again. That matches with the first equation. The third equation says 6 times t must equal 6, meaning t equals 1. If you make t equal to 1 in these formulas, you get point q back, just as you should. In two-dimensional space, if two straight lines are not parallel, then they intersect in a single point. This is going to turn out not to be true in 3 dimensions. And to see this, I'm going to have a bad drawing of a cube here, and I'm going to draw in 2 straight lines along certain specific edges of it. Because of perspective, I don't want to draw too much of these lines in, or I'll fool myself about something. One of my 2 straight lines is going to be this red line along this particular edge of the cube. That straight line in reality extends indefinitely in both directions, but I don't want to draw too much of it in, or I'll fool myself. This green line is along this vertical edge of the cube. I think it's pretty clear that firstly, these lines are not parallel to each other. Also, I think it's pretty clear from this drawing that they never touch each other. If you're sitting in a room someplace, look at one of the walls and think of the line formed by the ceiling and the wall that you're looking at. And then look at another corner of the room and think of the straight line formed by the intersection of the 2 walls you're now looking at, which will be a vertical straight line. Those lines are not parallel to each other, and they never touch. In 3-dimensional space, most straight lines do not intersect with each other, even if they are non-parallel. These equations represent some straight line in 3-dimensional space. I want to think about another line also. If I use the same letter as the parameter on both lines, it would be really easy to get confused about which line I'm talking about. So when I write my equations for my other line, they're going to be equations that are similar to this. The x, y, and z will be linear functions of some parameter, but I'll call the name of the parameter something else so that I can keep this straight. I'll call the name of the parameter lowercase cursive s. If you give me a t number, I'll get a point on the first straight line. If you give me an s number, I'll get a point on this second straight line. I want to answer 2 questions. Number 1, are these straight lines parallel or not parallel? And then number 2, do the lines intersect each other? A direction vector for that first line is 2, 1, -1, the coefficients of the parameter. A direction vector for this line, 1 times s plus -1 times s, 5 times s, 1, -1, 5. I have to ask myself, are these 2 vectors multiples of each other? Do they point along the same straight line direction? And I think the answer is pretty obviously no. I have a 1 there and a 2 there. If this vector were a multiple of that one, it would have to be 2 times that one. But 2 times -1 is not that number. So these vectors are not multiples of each other. The 2 straight lines are not parallel. If I were in 2 dimensions, that means I would have an intersection point, but it doesn't necessarily mean that in 3 dimensions. What I have to do is this. I have to see if there is a t value and an s value, so that when I stick the t value into these formulas and the s values into these, I end up with the same x, y, and z. If the answer to that question is yes, then I've found the intersection point. If no, if there is no pair of numbers, t and s, that will make that happen, then there isn't any intersection point. That is to say, I have to see if this system of equations has any solutions or not. There are lots and lots of different strategies for solving these kind of things. Before we get started, though, I just want to make an observation. I have three things that I need to be true when I put the appropriate t and s values in. The x coordinates, the y coordinates, and the z coordinates have to come up equal to each other if I'm to have a point of intersection. I've got only two things that I can move around or adjust, though, the t and the s. Usually when you have more equations than you have variables, you don't get a solution. So I made these numbers up out of thin air. I'm not expecting to get a solution. But then again, maybe by luck, I wrote down these formulas and maybe these lines actually do cross somewhere. It's hard to say. One strategy is to solve one of these equations for one of the variables in terms of the other one, and then put that into the other two equations and see what they say. It looks to me like the easiest one to work with is this third one. If you subtract 1 from both sides, you find out that the negative of t must be 5 times s. That is to say, t must be negative 5 times s. If I knew what the s was, I would multiply it by negative 5 and tell you the t. What I'm going to do is, in these first two equations, every place where I see the letter t, I'm going to replace it with negative 5 times s, and then see what I can do with that. So literally doing that, I end up with these two equations. Notice the first equation has only s in it, so I ought to be able to solve that first equation all by itself and figure out what s is, but the same comment applies here. Here's the place where I could find out that there's no solution. If this says that s has to take on a certain value, and that says that s has to take on a different value, then there is no s that will make both of those true, no t to go with them, and no point of intersection. If, by some bizarre chance, the s value that comes out of this equation and the s value that comes out of this one happen to be the same number, then you've got yourself an intersection point. You'll be able to figure out what the s is, and then once you know that, you'll know the t. I can put the t number in here and the s number in there, and I'll find out that I get the same point on both straight lines. I have found an intersection point if it goes that way. Continuing to be literal minded about this, if I take that first equation and do just ordinary algebra to it, I find out that the s would have to be negative 1/11. I take the second equation, do ordinary algebra to it, I find out that s would need to be 1/6. S cannot be both negative 1/11 and 1/6 at the same time, so there's no way to make these two equations true at the same time. There is no s that obeys this, there is no t to go with it, and we have no point of intersection. To describe the direction of a plane in three-dimensional space, we will specify a vector that we're going to call capital N. capital N sticks up out of the plane at right angles. Of course, there are lots of planes that are parallel to each other, perpendicular to the same N vector. To pick out one particular one, I need to at least specify a point of the plane. I want to think about what kind of equation a plane would have to obey. Imagine that we take any other point that lies in the plane, other than the known x0, y0, z0 point, and I form the vector between these 2 points. That vector lies completely within the surface of the plane, and n is at right angles to the plane, so n must be at right angles to the vector that starts there and ends there. We can identify 2 non-zero vectors as being at right angles, though, by saying that their dot product must be 0. And this is going to give me an equation. If someone were to give me an equation that looks like this, and I remember this line of reasoning, I take one look at it and I say, this is the equation of a plane. The plane is at right angles to the vector with components A, B, and C, and the plane contains the point x0, y0, z0. Some people like to rewrite this. Some people will even go so far as to just write this, since it's a constant, as another letter, D. So if somebody ever gives you an equation that looks like a number times x plus a number times y plus a number times z is some constant number, this is a plane. These numbers are the components of this right angle vector, and this number will pick out which one of those parallel planes that you're talking about, in one sense or another. So if someone asked you to write down an equation of the plane that contains the point 2, 1, 6, that's the x0, y0, z0, and is perpendicular to the vector 3, 2, 5, we know what we're supposed to do now. The components of the normal vector, the n vector, right angle vector, 3, 2, 5, are the coefficients of the x bit, the y bit, and the z bit, respectively. The thing that I subtract away from x, y, and z are the x, y, and z coordinates of the known point, x minus 2, y minus 1, z minus 6. If I was comfortable leaving it in that format, I'm done. If I'm not, I can multiply it all out and move the constants over to the other side. But even in the simplified form, something times x, something times y, something times z, 3, 2, 5, are the components of the right angle vector. If I have planes that are parallel, it's not necessarily the case that when I look at their formula and write the n vector down, that I'm going to get the same thing. It could be that I could have parallel planes and one formula uses a certain normal vector and another uses 2 times that vector, or -3 times that vector. But what I can say is this: I'll identify when planes are parallel when their right angle n vectors are multiples of each other. So for example, think of 3x plus y minus z equals 4. That's some plane. Also, 6x plus 2y minus 2z equal 9 is a plane. If I look at the right angle vector for the first one as compared to the second one, obviously the second one is 2 times the first one. This means the right angle directions for the two planes are the same directions. It could be that the second plane is just a rewritten version of the first one, or it could be that these two planes have no points in common. If you take the first equation and multiply it by 2, you'll see which way it goes. The first equation says the same thing as 6x plus 2y minus 2z equal 8. The second plane says 6x plus 2y minus 2z is 9. There is no point x, y, z that makes that true and makes that true at the same time. So there is no point in common between these two planes. These two planes are distinct parallel planes, like these are. These two planes are clearly not parallel. Right angle direction for the first one is given by 1 times x, 1 times y, 1 times z, while for the second one, 2 times x plus negative 1 times y plus 2 times z. In this vector, all the components have the same sign, and in this one they don't. So there's no way those could be multiples of each other. I'm going to have a plane that is tilted with respect to some other plane. That means the two planes are going to intersect in a straight line, and I'd like to figure out the line of intersection of these two planes. All I need to know is a point that lies on that straight line and a vector that points along the direction of the line. There's at least two different ways I could go about this. Way number one, do algebra and stuff and find 2 points that are in both planes. That'll be 2 points that are on the line of intersection. Then the question becomes, find a straight line that passes through those 2 points, and we know how to do that. So let's explore that first thing first. I'm not going to argue this logically, but it turns out to be true. If I have a straight line in 3-dimensional space, it has to touch at least one of the 3 coordinate planes. It has to touch either the xy plane, the yz plane, or the xz plane. There has to be a point on the straight line where either z is 0, or maybe there isn't. There'll be one where x is 0, and if there isn't one of those, there'll be one where y is 0. So I'm going to try to find some points that lie on both planes by setting one of the coordinates equal to 0. X plus y plus 0 would be 1. 2x minus y plus 2 times 0 would be 4. If there are x's and y's that make both of those happy, I'll set z to be 0, and I'll have a point that lies in both planes, a point on the line of intersection. If you add the two equations together, the y's cancel out. I'll have x plus 2x, which is 3x, needs to equal 1 plus 4, which is 5. X needs to be 5/3. Now, one needs to be a little bit paranoid here. I'm looking for a point where z is 0. I don't really know if there is such a point on the intersection line. What I've found out is if there is, its x-coordinate would have to be 5/3. but both of these equations have to be happy, and there's a y in them. If this said y has to take on a certain value, and this said y had to take on a different value, then my z equals 0 strategy will have let me down. So let's see what we can do. I'm going to see what it would mean when x is 5/3 for this equation to be true and for that one to be true. Yes or no, do I get the same y value? The first of my two equations, x plus y equal 1, after a little bit of algebra says y must be negative 2/3. Using x equals 5/3 in this equation ends up telling me that y must be negative 2/3. So we have found a point in the line of intersection. X will be 5/3, y will be negative 2/3, and z will be 0. This P is a point on the straight line that I'm after. I can now find some other point. Maybe there's another point on the line of intersection where, say, the x coordinate is 0. In my equations, set x equal to 0, that says y plus z needs to be 1, and negative y plus 2z needs to be 4. As before, I'm going to add the equations together. This time, the y's will cancel out. And I find out that 3 times z must equal 6. Obviously, z would be 2. Now I need to figure out what the y is. From that equation, y plus 2 would need to equal 1, so that y would be negative 1. And in this equation, negative y plus 2 times z, 2 times 2, 4, needs to equal 5. Negative y would be 1. Y would be negative 1. So I have another point in the line of intersection of the two planes. X is 0, y is negative 1, and z is 2. The vector from P to Q will be a vector parallel to my straight line. That'll be my v vector for the straight line that I'm after. A direction vector for my straight line is negative 5/3, negative 1/3, 2 in component form. This is a vector. It's an arrow. If I felt like it, I could just leave it like this and work directly with it. Or if I felt like it, I could multiply this vector by a number, and it will still point along the same straight line direction. If I multiply by a positive number, it literally points in the same direction as it originally did. And if I multiply by a negative number, it points along the same straight line direction, but is orientated the other way. Obviously, I'm going to multiply this vector by negative 3 to make things look a little nicer. Although I can't stress enough, if I wanted to, I could have just left it like this. So here is a vector that points along the direction of the line of intersection of the two planes. If I want to write down equations for that straight line, all I need is a point on the line. I could either use that point or that point. I feel the need to comment, this point has fractions in its coordinates, and I cannot get rid of those by multiplying through by 3, because that's not a vector, it's a point. So we could use those, but it seems to me to use these coordinates would be easy, because they're whole numbers and stuff. It makes no deep difference, though. So there is the equation of the straight line formed by intersecting the two planes that we started with. Another kind of geometry question we can now answer is this. If I have a plane with a known normal vector, and I have a point P that is not in that plane, if I were to travel from point P to the plane in as direct a path as I can manage, a right angle direction path here, how far apart is point P and point R? What is the distance between them? That would be the perpendicular distance from point P to the plane. If I had an easy way of getting my hands on point R, this would be a triviality. I take the coordinates of P, the coordinates of R, feed them into the distance formula, and out would come my answer. Unfortunately, I don't have an easy way of doing that, so we're going to resort to trickery. First comment, if I formed the vector from P to R, it would be a multiple of the capital N vector, because both of those are at right angles to the plane. Secondly, I'm going to take another point in the plane and call it Q. If you think back to how we defined addition of vectors, the vector from P to Q, you could think of it this way. It's the vector from P to R plus the vector from R to Q. I know something special about vector P to R, though. It's a multiple of the N vector. I know something special about R to Q as well. It's at right angles to the N vector because N is at right angles to the plane and vector R to Q lies in the surface of the plane. If I could somehow get rid of this vector from R to Q and also simultaneously somehow figure out what the C is, then I would literally know the vector from P to R without ever finding out what the R is. This is kind of like a magic trick. This immediately tells me what C is. C is the dot product of the vector from P to Q with the normal vector divided by the square of the length of the normal vector. It's worth mentioning that if someone else had used a different version of the N vector that pointed off in the other direction, that would just flip the sign on this thing. PQ dot N might be positive or it might be negative, but either way, we'll figure out a way of dealing with that. So crazy though it may seem, I've managed to find the vector from P to R without ever stating what R was. Moreover, the length of this vector, the vector from P to R, is the perpendicular distance to the plane. One of the things, though, that we figured out about magnitudes of vectors is this. The magnitude of a number times a vector is the absolute value of the number multiplied by the length of the vector. This n is that n. The bottom of the fraction is already positive, so to take the absolute value of the fraction, I'll just stick absolute value signs on the top. And lastly, I can cancel out one factor of the length of the n vector and get my final result. If you give me a plane with normal vector n and a point P that is not in that plane, and I'd like to know the perpendicular distance from point P to the plane, here's what I do. Find a point of the plane, Q, any point in the plane will do. Calculate the absolute value of the vector P to Q dot product with n, divide by the length of the normal vector, and you're done. There's the answer. So, for example, think of having the plane x plus 2y plus z equals 1, and the point P with coordinates 1, 2, and 3. 1 plus 2 times 2 plus 3 is definitely not 1, so this point does not lie in this plane. I'd like to calculate the perpendicular distance from point P to the plane. In view of what we've just said, firstly, I need a point, call it Q, that lies within the plane. I need a triple of numbers, x, y, and z, that obey this equation, and I don't care what they are as long as they obey this equation. So I'm going to be as lazy as I can humanly be. I'll make y and z both 0, and I'll make the x 1, and that'll do it for me. By now, end minus start ought to be very familiar to us. So the vector from P to Q has components 0, -2, and -3. The right angle vector, the n vector, has components that are equal to the coefficients of the x, the y, and the z in the equation of the plane: 1 times x, 2 times y, 1 times z. There's my n vector. I need to know two other things. I need to know the dot product of those two things so that I can take the absolute value of it and stick it on the top of the fraction. Then I only need to know the length of the n vector, and I'll have my answer. The perpendicular distance is 7 divided by radical 6. We could rationalize the denominator or write it in decimal, but by this stage of the game, that's just cosmetic. There's your perpendicular distance. The last of our analytical geometry problems is this. Suppose I have a straight line, and I have a point P that isn't on that straight line. I'd like to know the perpendicular distance between P and the straight line. Unlike planes, which have a right angle vector, straight lines have vectors that point along the direction of travel. The general strategy that we're going to follow, though, is almost exactly the same. So let me draw some stuff in here. Just like before, we'll pick a point in the set of points of interest, which is now this straight line. I can then form the vector from P to Q. If R is the closest point on the line to P, I could also think of getting from this point to that one by first traveling from P to R and then traveling from R to Q. So we can write our P to Q in this format. I know that P to R is at right angles to the V vector, and R to Q is parallel to it in the sense that it's a multiple of the V vector. I can easily calculate this. The magnitude of that vector is what I want, so I want that to stay around. This is the part that I would like to somehow get rid of. I can't get rid of it by doing a dot product with V, though. This term would just be constant C multiplied by the square of the length of V. But I've got another kind of vector product that I can use. C times V points along the same straight line direction as V does. When you take a vector and cross product it with a vector that points along the same line, the result is the zero vector. So this will get rid of this term for me. This is kind of a strange thing, though, because the cross product doesn't give me a number back. It gives me an arrow. We have no notion of how to divide one vector by another, so it's not as though I can divide the v vector out here and find something out. What I'm really interested in is the length of this p to r vector. So I'm going to do something that will let me figure lengths out. One of the things we previously mentioned is that the magnitude of a cross product is the length of the first vector times the length of the second vector times the sine of the angle between them, and p to r is perpendicular to v, so this angle would be 90 degrees. Sine of 90 degrees is 1, so this factor can be omitted. This says that this quantity is the length of the v vector times what I'm after. So the way I'm going to get the perpendicular distance to the line is I'll pick a point Q on the line and form the vector P to Q. I'll do the cross product with the v vector and then calculate the length of the result. Then I'll divide by the length of the v vector, and there's my answer. As an example, I'll have the straight line x equal 1 plus 5t, y equal 2 plus t, z equal t, and I'll also have the point P with coordinates 1, 6, and 3. If I wanted to be paranoid, I would check and make sure that that point isn't actually on the line, although if I didn't do so and found out that the perpendicular distance was 0, I would know then also. In any case, if this point were on this line, there would have to be a place where z is 3. That would mean t is 3. 2 plus 3 is 5, and 5 isn't 6. So point P is definitely not on this straight line. To get going, I do need a point on the straight line. Any point will do. So set t equal to 0 here. Do the usual end minus start. The direction vector for the straight line has components which equal the coefficient of the parameter, 5 times t, 1 times t, 1 times t. So the v vector that I'm going to use has components 5, 1, 1, 5i plus 1j plus 1k, if you like. I have to calculate the cross product of these two vectors. Assuming I've done my arithmetic correctly, the cross product is negative 1 times I minus 15j plus 20 times k. The top of my formula is going to be the magnitude of that. The two norms involved are easy enough to calculate. The perpendicular distance is the square root of 626 divided by square root of 27, which in decimal is 4.815 to 4 significant figures. We also need to look at some surfaces, but given my drawing abilities, I think it's going to be better to refer you to a video that I previously made about such things. Having said that, this completes our elementary analytical geometry, and in upcoming work, we'll actually begin doing calculus again. Until then, I hope everybody has a good day. I'll talk to you again soon.